Hello everyone, September 27th. Alright, let's do today's challenge first. Remove nth node from end of list. Given a head, remove the nth node from the end of the list and return its head. N equals 2, so 1, 2, okay? 1, 1, okay? I mean, can we not do it twice? Oh, I remember there is a way to do this. Nth node. Yeah. I just need to have, that's just 2, then just go, let's say, 1 star from here, 1 star from here. I wanted to land at something right before, right? So I want the pre to land here when the end is here. Right? So, oh, but it could be the last one. If I want to delete the last one, it has to be here. I'm thinking. So 2, I can say root. What if I delete this? So the star will be here. And I'll go 1, 2. Okay, so 2 is here. And I will start with the dummy. So we go 1, 2, 3. 1, 2, 3. So when the other one lands the last node, we end in here. Then we say we'll delete the next one. Delete the one next to it. Okay? The edge case is always the edge case. Let's see, edge case, let's say 1. Okay? And we have stars here. And then we say we do 1. The end is here. Then we say, then we delete this. Okay, that works. And 1, 2. If we start here, and then we do 1. So we move 1. Oh yeah, I think this might work. So it's 20. And one day we'll go back to that problem. Anyway, so we're gonna have a dummy node. Dummy equals what? List node next equals head. Okay, and we say pre equals dummy, pre, and what's current? Current depending on how many times we move, right? And so p equals current equals dummy, and then we say while n current equals current.next and minus equal 1. So we do 1. So current equals this, n equals 1, current equals this, n equals 0. Okay, so now we say while current.next, current equals current.next, pre equals pre.next. Okay, once we get out, we just go pre.next, because we need to delete pre.next. Right, so pre.next shall equals to pre.next.next. What if it's the last one? No, it won't be, because current is the last one. So pre.next definitely exists. So pre.next, .next, right? Pre.next, .next. And that should be it. And we can say pre.next, like the temp equals pre.next, and then pre.next equals temp.next, and then temp.next equals none. And we're going to return dummy.next. That shall work. Let's give it a shot. Test case is pretty good. Yeah. I think that shall work. Let's give it a shot. Oh, C. Okay, so that's that. Yeah, dummy node, and yeah, I remember how to get there. That's the part I remembered. I remember that to find the nth node from the last, we just need to use the nth node from the start and have two nodes moving at the same time. Then when the when one node reaches the end, the other node would reach the nth position from the end. Of course, in reality, in actual implementation, we want to land at one node prior to the nth node from the end. And we need to use a dummy node. But these are just implementation details. Yep. That's that. Not too shabby, right? Not too shabby. Okay, so we're done with this. We can take a look at our method previously. So this is the third time we've done this. Third time. And it has really good test cases, so it's really impossible to get it wrong. This is 208 test cases. I think this is the fast one. We have dummy, you have this, this. Yeah, that's exactly what we use today. What's this method? I have a size. Not the best method. 208 again. I mean, I don't know, like this is maybe a little bit slow. And we also did this one, which, no, it's good because you need to really delete this node, right? So you have to do this, but it's not really necessary. All right, anyway, so we're done with this. I didn't figure out anything with this, so I think I'll have to, oopsie doozy, I just clicked the wrong thing. Yeah. This day and age, and this time, very unfortunate. I don't think I can ever do another contest. I'm going to look at the hint, because what I have is no good. Can you process nodes from smallest to largest value? Ooh, that is the opposite of what I thought. Smallest to largest. I was going from largest to smallest. Okay, so what's going to happen if we go smallest to largest? If we go smallest, then what does it mean? Smallest value, and everybody's larger than you, so you can belong to any path. And we look around and see. So we have the smallest value, right? And then we branch out, and then what? Well, for one thing, the smallest value will definitely not be made into a good path. So we need a larger. So smallest, we find a larger one, right? Hold on. I can say if we have a smallest and it only has one path, then it's not going to be in any of the thing. So we can remove that without issue. If the smallest one has two or more paths, then it is possible that it gets connected, right? And then we'll look at what it's connected to. Okay, so it connected to a value, and if that value is one bigger than it, are we saying is it possible for the second smallest to form a path? Because the second smallest, the only possibility for the second smallest to form a path is if it goes through the only smallest. So if I find the smallest, we find all the smallest, okay? That's how we find all the smallest. And we find the second smallest. And we want to see, so the only possibility the second smallest will reach via the smallest, which means the smallest must So we find the smallest, then what? Well, yes, the second smallest must use the smallest to, so we have the nodes, right? We have the nodes. And how do we know they connect? Like, the path must be between them, right? Or we can start from 2, right? We start from 2 and then we start traversing. If at any point we hit a node that's not 1, that's end. We can now go from there. And if it's 1, it has to be another 1. Want to try that? So if we start from 3, then we have 2 options, right? It can be 2 or it can be 1. It just cannot be larger. I mean, this is exactly, it has nothing to do with this method. It's just a naive method. But we can say, as we do already find a path. Yeah, let's say from 1, right? From 1, we can only go to 1. So we're just trying to search and then we'll find some paths, right? So we can say starting from a certain path, starting from a certain node will lead to the other nodes. We start from other node will lead to the other nodes. Starting from any one, let's say we have a long string, and then we say these nodes are connected, right? These nodes are connected. Okay. And then we go from 2. And if we get to a 1, we see if this 1 has any connection to it. We see if this 1 has any connection. And if it does not have but we can go with 2 as well. Nope. Keep going. Try to build a graph from nodes with the smallest value to the largest value. So you're saying from the union find. I was thinking about union find. Hold on, let me think. Union find. I was thinking about union, like all the things that you can reach, we can union them. Let's say we have the smallest, so 1, right? And we try to traverse from 1. And we find, like, if it's on a path, we put it in a union, right? Okay, so from 1, we go, 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 go. If it's by itself, that's by itself. If not, then they're together, right? And they're together. Okay, and then we can count the number of unions, right? The number of unions. Okay, so that's 1. Now we start from 2. When we start from 2, we can only union with 2 or 1. So we traverse from 2. If we hit a 1, we'll union with it. But we union with it, then what? It has to end in a 2. And when you union with it, then you know where this can lead to, right? And the number of nodes is a lot. 3 times 10 to the 4th. So I'm thinking like if the original one, we have a union, right? And say we also know who is in this union. This we can do. This we can do. We can put who's in this union. By just going through find its parent, and we can find all of those that has this parent. Okay. Yeah, we can have another data structure in the union find so that we always know who belongs to a parent. Now when we find a parent, like if let's go from 2 and its next one hits 1, right? And we know everything that 1 connects to. So we just go through that list. Okay? We go through that list and trying to see if their next value is going to be a 2, right? Because they are all 1s. We just go from there, trying to see if they have a thing that's 2. Okay, if they don't, then we fail. But if they do, then we'll union that as well. Then next we try 3. Again, we go through everything, try to see if the value is smaller than 3. If it is, we find its parent. And then from the parent, we find all the nodes that's on the same path. And how do we avoid? Well, we can put the parent in it. So if the same parent, it won't be double counted. Okay. So 3, we try to find, okay, and values is 3, 1, or 2. And if it's a 3, if it's the same, we go to the same. And we just union them. It's okay. Right? And if it's smaller, we go there, try to see where they can lead to. So every time we'll go through and if we have exhausted, because a node, like if I'm 3, right, I go to a node 1, and we have traversed all the nodes that 1 connected to, and none of them is bigger than the current value, right? Which means, wait, no, it's bigger, because I need to find 3, right? If it's always smaller, then this node is useless for future, so I can remove it. I can remove it. So not only union find, but we will update. We'll update the group as well. Because each time when we do, right, we go through that list. We're trying to find the parent. Right? We're trying to find a parent that we go through all of them. Yeah, we go through all of them. And if we go through all of them and nothing happens, then we're going to remove it. So the next time we don't have to go through the same one again. Okay, this is very complicated. Very, very complicated. But we're going to give it a shot. Wait, hold on. Nah, I don't think so. Let's try this. And once again, give us n? It does. Self.parent, self.rank. There's one more thing. Self.group. I'll call it default dict for the set. Okay. Then def find if self.parent x is not equal to x, self.parent x equal to self.find self.parent x, and return self.parent x. That's fine. We just look for it. We just look for, oh, hold on. If it's not equal to, we have to update group, right? So if it's not equal to x, right? If it's not equal to x, then we say pre equal to self.parent x, and then we have this. So we say self.group pre.remove x. So no longer in this group, and self.group. Actually, we can just go here. This is interesting, very interesting. So we remove it, we update it, and we're gonna add, and then return self.parent. Def union x, y, ruling value. Okay, we say parent x, parent y equals self.find x and self.find y, right? We say if px is equal to py, then we return false, right? Otherwise, we say if self.rank px is larger than self.rank py, then self.parent x, right? Self.parent. Wait, hold on. I remember this is where we got wrong last time. No, self.parent px. So px is parent, not x, because x is parent is px, right? So you don't have to do. What we need to do is get, actually it's not, py shall equal to px. So py is parent, because px and py, they're not the same. So we assign py's parent to be px, right? And when we do this, okay, so right now, y's parent is py, which means it will be assigned. So now I want to change. So x doesn't change, but y need to change. So we say self.group py.remove y, and we set parent py equals px, right? And then we say self dot. Do we need to do that? We union them, right? I feel like this already handled it. Let me think. I mean, what we can do, let's say, we update this, and then we just say self.find y. By doing this, we're calling this, because I'm changing py's parent to px, right? And then what we're saying, and py, this is py's parent. The y's parent is py, right? So we find y, and then they're not the same. And then remove, but this one can be the same thing. So I just remove and I add. If they're not the same, okay? So when you say pre-parent equals self dot parent x, right? And then we do this, and we say if self dot parent x is not equal to pre-parent, that's when we do. Otherwise, we don't do. Because a lot of times we don't have to do. So pre-parent, right? So now this I change. Right? I change to px. So if I find y again, this will still be py, right? And then this will be py. And then I'll find self.parent py, which is basically px. And this will return a px. And then self.y equals px. Px is parent, which is px. So this would be px, and this is actually py is not the same. So I do this, and then we return. So yes, we find after we've done this. I mean, actually, we can just do this find x, find y at the end. Well, why do you do it twice, right? It's not really necessary. So let's just do it here, right? We can elif. This one's smaller than. Ooh, hold on. And self.rank px. No, it's no ranking. Not yet. This is self.parent px equals py. Py is bigger than self.find y, find x. We're just updating the group. And else they're the same. Then we just say self.parent py equals px, self.find y, and self.rank px plus equal 1. And this will return true, right? Okay. I think we're good. Group. No. It should be for I in self dot for I in range n, right? Because group they have themselves at the beginning. So I will be a set of, actually I think it's just like this, right? Hold on, I'm not 100% sure. A equals, let's say 1. What's this? Yeah, it is set. So we set this one to be a set group, right? This is the beginning. And then we can find they're the same, that we don't change. And we union, then we do. Okay, so that's the DSU. So now what? Now we're gonna go from small to large, which means we are going to we're going to have the We have this, probably want this one as well. Okay, so I have the adjacency matrix, we have we have the adjacency matrix and we have the mapping, so we know where to start. Okay, so now we're gonna go from the smallest. So for each one, and we're gonna kind of have to have a DFS. So we have a DSU as well. Len vowels. Okay. Now I think I need a DFS, which is traversal, right? Traversal. And I think that's also when we have to add the result. So self.res equals. I just realized this is just n. Come on. All right. So the DFS is we start from this node, right? And we go to see if there is any node that has the same value as I do, right? So we will go to my neighbors. If the value is smaller, then we will go to, and we will find its parent, right? If its value is smaller. And if it's equal to myself, I will union that, and that will count. Right? I'll union that. Hold on. So for each node, we have a node, right? So for each node, go through its neighbors to see if there are anything smaller than me, right? If there is, then we do a bunch of things trying to figure out. And the goal is to paths. Paths. Could be parent. The parent might change. That's the thing. The parent might change. I think again. Parent set. So for current node, let's say I have a parent set. Not sure. I'm just trying things. Okay. And when I go through everything of the same value, now we're gonna count. Okay, so parent set. I don't think I'm doing anything here. So what do? So the node is a value, and then we know its value, right? We know its value. So what we want to do is look through, right? We're going to look through and we say for child in that node. Oh, in this case, then it can be a list. We don't have to do this. We can append. Okay. So for child, right? When I say if Val's child is equal if Val's child, right, is equal to Val's node, that's immediate, right? It's immediate. Then we say DSU.union child and node, right? We union them and parent set dot add DSU.find child node. Okay, it's the same. Else if Val's child is smaller than Val's node. Okay, if the child is smaller than the node, then we need to first see if, then we go, what, we find a parent, and we say the group G equals DSU dot group G, DSU dot find child. So we find a group, right? And we say if child is in G, right? Because child is not in G, which may be kicked out. That means it will never reach a value that's equal to no, which means go this path is a no-go, right? Is a no-go. Oh, hold on. If this cannot reach, oh yeah, because if then something else will be in it. Yeah, so by pruning, we will be able to keep the group as small as possible. Yeah, the group will be small. So if child is in G, that means, but anyway, if child is not, it doesn't really matter. I just go through G. G is the one that has potential, right? Then we say for potential in G, right? For potential in G, what do we do? We need to remove. Not even sure if it's not allowed. So we have to go list G. Right? So now we can do G.remove. So for potential in G, these are what we can lead. Then we have to look around G, right? When I say for CC, for C in potential, mat potential, right? And we say if val C is equal to val's node, right? If they are the same, then what do? Then we say val's, holy crap, then C can also be union. Hold on, we haven't union yet. C, a potential, we have a thing which is equal to, right? And if that's the case, then we will we can prune mat. Think about it. We can prune mat. If it's not, then we can just delete it from mat. Now this seems to be attractive again. Right? This seems to be attractive again. So I don't have to, I can even just say, but we have to go through all of these. That's why I don't want, because you can reduce the amount you have to go through. We can, how about do both, right? We do both. We'll remove here and we will do this as well. Okay, we'll say if vowels C is smaller than vowels node, right? Then there's no hope. This one cannot be used for anything else. Then I just say mat potential dot remove the C, because it cannot be used. Elif, this is equal to, okay? And this is interesting. So we have equal to, which means we can union that and union myself as well. This is when we union. I'm going to say dsu.union node and so potential and node, and dsu.union potential and C, right? We union the both, and parent set.add dsu.find node, right? So we can union them, right? We union them, but once we do that, it's also remove, because if it's this, then it's useless for future, right? For future. We're talking about potential, right? We're talking about potential, the potential, because potential, we say we can lead to this, right? And this one's already added, but potential don't need potential anymore, because potential doesn't need this link anymore. So we can say mat potential dot remove C. Else, if it's bigger, then we ignore, right? And then we just keep going. So once we're done, right? Once we're done for potential in this, right? And we say, because if potential has removed all its links, right? So no more links to potential. And we say if mat potential, if not mat potential, so everything got removed, then we say g dot remove potential. So the next time potential will not be called again. So that's if it's smaller, right? So we do that. And what if it's bigger? Well, it's bigger, we just ignore, right? If the child in my current node, if it's smaller and it's equal, smaller, and have something bigger, then we just don't go there. There's no point. So that's what we do, and that's a DFS, right? So now we can say for V in sorted vowels map, right? So V is the smallest value. Then what do we do? we get, right, for v, so for the smallest v, then we have parent set equals a set, and for node in vals map v, for each node we call DFS node and parent set, right? We call that, and once we call that, we can say self.res plus equal to parent set. Yeah, this is what I'm worried, right? As the previous set, I think it's stabilized, right? Everything's stabilized. But would it be possible that we'll double count? That's what I'm worried about. Because we union, so they will have the same parent, right? And I'll add the same parent. So once I reach the C, right? If I reach the C, and then it will look around, but then it will be the same thing, right? Child, if it's the same, there won't be double count, and if it's smaller, we get a group, which is fine, and we will try to see its next value, right? We'll try to see its next value. And I'll ignore, right? Well, and ignore the ones that's the same value as me. So we can actually ignore the value the same as me. So we can say if vals potential is smaller than vals node. It has to be this because they might be the same. If they're the same, that means this path we have already encountered. So we just don't do it. So it has to be smaller. We try to find new potentials. Say map potential. So we're going to do this, and this is going to be length parent set. And I'm going to return self.res. Oh my god. Let's try. 2. Of course. Set size changed. Ooh. Yep. Listed. It's pretty close. We're overcounting. Wow. How do we debug this? Well, everything by itself. So we have 1, 2, 3, 4, 5. So we basically found 2. Well, actually, it should only be 1. Interesting. Why don't we check this? Print dsu.parent, print parent set, right? And of course, print v. So we know what we're talking about. Okay, so v is 1, and of course, there's nothing. V is 2. Ooh. V is 2, I have trouble. V is 2. The SU, the parent is, so 0 is 0. That's 0, right? 1 by itself. 2, 3. Say these belong together. That is not true. That is not true. Okay, there's something wrong here. So let's say our node, because only 1, 2, right? So node is 2, and child is this and this, equal, no, but it's smaller, okay? If it's smaller, then we go to group. These are not the same, so we find which one, whichever one. So we find this, right? Else this is smaller for C in list, so basically this and this. If val C is smaller, oh, val C. If C is cannot equal to node. So if they're equal to node, yeah, be like this. If C is not equal to node, then we do this. Then we only 5. Damn, man. Now 2 is right. Now 3 have trouble. 3 is starting from here. And oh, well, that is true. Because they no longer group together. Holy crap. They need to group together. Yeah, the smaller one need to group together. Hold on, let me try it again. So if the same, they group. Fantastic. If it's smaller, then no, they have to group. Right? So for potential in list G, right? If potential is smaller, then I have to group them together. That's what I think, right? We have to group potential and node. We have to group them, right? We have to group them. So if the potential no, we have to group with child. Hold on. This is a little bit. So if this is smaller, then we have to group child and node. Okay. So the same thing. We'll group child and node, and we can actually say if val's child is larger than val's node, then continue. Otherwise, I'll group these two together. And if it's the same, we do this. If else, then we'll get, right? We'll get the group, and I look through in the group. Here's the potentials, right? The potentials cannot be the same as node. And then from the potentials, we find the next one. And the next one cannot be node, but it has to be. And we don't have to do node again because we've already done it. Now, then when we say when you union child and node, and then give you true, or give you false, that means it's already in it. Right, it's already in it. Is it possible? I go here, I'll find another path. But if this one's already in it, and there's another path, it will have been found already. right? It will have been found if child and node is already together. If they're already together, that means someone in the past has grouped them already. Here, right? That's the other union. That's the only other union is here. Someone has reunioned them already, so it's already part of the path. So what I can say, if not, then continue. So it's already, so node already considered in this path. And then only if it's false, right? Only if it's true, which means we did union the two. Then we do this, or we do this. And I have the potential. If it's smaller than the node, I have the potential. Oh, you gotta be smaller than the node. This is, yeah, because if it's larger than node, I don't even union them, right? So if child is smaller than the node, then in this group, it must be smaller than the node. It cannot be larger than the node because the group is all the nodes smaller. Hold on, do this again. Yeah, so child has to be yeah, I don't think this is necessary because everything, because we go smaller to big, right? So inside the group, it's always going to be small. And we union these two because child's value and node's value, child's value is smaller equal to node's value, right? And if that's the case, everything in it is going to be smaller than node. So this is not necessary. So we can directly go, so for potential, and then for each potential we list its child. And if it's not equal to node, we will check its value. And if its value is smaller than node, which means there's no point of going there anymore because it's small, right? For that path, we don't have to go because if it's small, it must be in group already. So I remove it. And if it's equal, I'd also remove it, right? So we can say if vals C is larger than vals node, right, then continue. Otherwise, I'll remove the C, all right, and we say if it's equal, then our union C and potential, or C and node, doesn't really matter, they're the same thing. Okay, so if that's the case, okay, this one we pass. Let's try these two. Oh, they all pass. Okay, this is the one we failed yesterday. Wait, oh, dummy. Set changed. Where? Which one? Mat node. Huh? How? Child in mat node. I never changed the mat node. This is just value. It's node's value, right? So if the child is smaller than the node, so the child is smaller than the node, we'll look for a group. Okay, so that's the group. And because I already union them, so the group will have it. So for potential in this, yeah, I have to say if potential is not equal to node, because node is in potential. So we have mat potential.remove. Okay, so oof. Can I copy this one? Basically, if this one can be correct, then we're good to go. So maybe I have to consider? I don't know. I got a timeout. Yep. That take way too long. Okay. So what we can do is, let's say we don't is it increase. We'll increase a little bit. Okay, we increase a little bit. Maybe I don't do this. Oh, it'll take a long time. Still. No. I'll put these back. thing is, there's a huge difference. What if potential is smaller than? Not potential, is C. Shouldn't be, because we start from this, right? And if it's smaller, I'll union them already. So they should belong to the group. I think I know why. They belong to the same group. But there could be multiple. Damn. So for each group, God, because there could be multiple inside a group, and then just we have to choose. I see. Now how do we handle this? So for each parent, okay, so for each parent, we say for P in parent set, right? For P in parent set. But the group is not, darn. We need to go through, oh my God, I'm gonna go through the entire thing. Nope, because the current node will never be deleted. Only potential gets deleted. So for P in parent set, we say dsu.group P, right? We just need to know how many. So for I in this is a node, and we say vals I this value equal to v. So I have an n already, right? Count, let's call count. Count equals sum this thing. So these are all the nodes of the current value that's in each parent. And self.res need to plus equal to count minus 1 times count divided by 2. Then we don't do this. Oh, gotta be kidding me. Still not right. It's actually even smaller. That's bonkers. How could this be even smaller though? I'll never remove node. How about we remove only when it's smaller? If it's smaller, then we remove. If it's equal, we don't remove. This is not going to be right. Yeah, I think I'm gonna call it. Ooh, ain't right for the other ones as well. All right, now we can talk. Now we can talk. Let's see. How? Parent set is 0. So we go through parents. Maybe we should do group as well. Zero only has 0. What? What about the 2 3s? Oh, this is wrong on so many. The parent, everything is the same. Oh, that's actually correct. Everything is the same because they all belong together. This is actually correct. And it's going to be 0. So what the problem is the group. I think the group is not working. Like the hell, the group is not working. We union the 2. So the first time we union the 2, we'll find. And initially they will be the same, right? So I'll just return it. And they're not the same. And the rank is the same. So we set one of the parent to this and increment the other's rank. And then we try to find y, because I change py. Py will just be y, so that would be x, right? And that would be 0. And I find y, okay? Then I find y, and parent y is not equal to y. Yeah, it'll be not equal to because I changed it, so it'll be px. Oh, I already changed it. It's pre, that's the current. I think I find out why. Holy crap. You know what? I think I should just do it here. So py dot remove y and self dot group px dot add y. And this is reverse px dot remove x and py. Okay, so when I do this, it will be 0 to 4. 0 to 4. Why is this one not in? Gosh, man. Yeah, seriously, why is this one not in? Apparently it's been removed, right? Apparently it has been removed. Why do we remove and potential is not equal to node? And when a node comes in, like when I have 0 to 4, this one remove, I don't really care. But 1, right? 1 comes in. I think 1 comes in first. You know what? I might want to so definitely now when I'm doing this, right? If I'm doing this because I union them, right? So 1 is inside. And then with a potential, it has to be not equal to node, right? So that's fine. That's when this one comes in. And then we go to this one, right? How about, let's say val's pot is not equal to val's node. They cannot be the same. Yeah, if they are the same, then, yep, if they are the same, right? If the values are the same, then no, like what you're gonna do. What you want to go is find a smaller one that can go out to reach the one that is the same. If they're not the same, then we go to get its things, and I say if it's smaller, then I remove. But if it's the same, right, we keep? Do we keep or do we not keep? It's the branch out. Now, if we branch out, we don't have to keep. I still think if we branch out, then there's no need to keep this from the matrix, right? From the matrix, because C is inside, so we don't have to keep it. Okay, I'll go back to the old one. So larger than, then we continue. And then we do this. Yeah, see, we reduce. And it's not polluting it. Okay. Getting closer. We're getting closer. All right, we're gonna end it today here. We're getting closer. We are getting closer. I'll see you guys tomorrow. Adios.